So I'm going to switch this a little bit, and I'm going to make this more random. I'm going to say create binary. And to create this binary, we're still going to want that bin list. To create this binary, well, I will also change this, create binary. We want to think of a length 4, right? But maybe length 4 binary, maybe length 5 binary, maybe length 20 binary, right? So we want to set a length, and I'm just going to call this length of our binary list. So maybe to be more accurate, I'll just call this create binary list. Create binary list. All right. So I need a random draw here. And I'm not going to go ahead and write a random, I'm not going to write a pseudo-random number generator here. That would not be a good use of my time. You know, pulling out some assembly language and seeding it and, you know, doing a series of divisions that lead us to a random number, a pseudo-random number. Instead, I'm going to say from random import choice. So choice is a function that will, if you notice here, it chooses a random element from a non-empty sequence. What does that mean? It means that I can say okay, what is my sequence? I'll call it seq. And a list is a type of sequence, right? It has order, and it has a number of values. So we've been calling these collections. We've been calling them data structures. A list is sequential. So the only two choices we care about are 0 or 1. And so that's where we're going to make our choice from. We're going to make a choice from 0 or 1. All right. So I can just say for, I'm going to do this. This means that I don't care what this is. I don't care what this value is. You know, it's going to be a counter, right? It's going to be 0, 1, 2, 3, 4 up to the length. But I don't care what that number is. So for I in length, sorry, for I in range, the length of the list that we want to create, I'm going to say bin list dot append, and I'm going to append the choice of the sequence. Okay. And I'm just going to return that bin list. This is only creating a single binary list. And let's prove it's doing something. I'm just going to print this. I'm going to set my length to, well, we'll set it to 4. And I'll comment the rest of this out. And we should see a binary list unless there's an error. And we do. So 1, 0, 0, 0. Okay. Run it again. 1, 1, 1, 1. 1, 1, 1, 0. So, you know, we could do this 15 times or 16 times. And we could compare those results to what we were seeing before, right? Like 1, 0, 6, you know, 6 2s, right? We could do that. But that's not a good use of our time, right? We have a structure that can create relations, that we can associate counts with certain sums, right? And that's what we're going to do. Actually, we already did that. But we need to create a larger pool, right? We need to take a sample of some size here. And I'm going to start off. So let's, I'm going to start off with a very small sample. And I want to do this to inform an idea that we're not going to touch on today, but I think you'll sort of see it. Okay, so I'm going to make a function called binary samples. I could call it create binary samples, I don't know. And I'm not going to pass anything into this. Oh yeah, I am. I'm I'm going to pass in the number of samples, and I'm going to default this to 16. So if we're generating 4-bit binary in a sort of closed form procedural way, not in this sampling way, there are 16 possibilities. So if I do this, we're going to be able to see what this looks like with a sampling approach. So I'm going to say def binary samples, num sample 16. I'm going to, you know, bin list? No. Bin samples, bin samps. How about that? And let's say for, I could write this as a comprehension. Some of you know comprehensions. I'm doing this as for loops because I want to still stay within the realm of accessibility for people who haven't seen comprehensions yet. So for whatever in range the number of samples, we're going to append a sample. So I'm just going to append create binary list. And you know what might be helpful here? I might actually put another parameter in here. I'm going to do length, and I'm going to default it to 4. So now, if I call this, I'll just do this. If I print, you know what? I'm not going to print this. I'm going to set it into here, and let's see if it just works. I think it should. Did I not return it? I may not have returned it. I did not. Okay. So return bin samps, right? Need to return it. And now, when I print this, we should see that nice little graphic. Unless there's something terribly wrong, and there probably is. Let's find out. Okay, there wasn't anything terribly wrong. This didn't come out exactly as we would have expected, though. You know, if you're looking at this, these counts are out of order. There's a reason for that, and I'm going to fix that right now. So we'll get another read on this in just a second. So for key value in this binary dictionary, it turns out that dictionaries do not guarantee order. They are not like lists. Dictionary items do not have an index, okay? So with this, I can sort this. And the reason I can sort this is that dot items will actually, it will return a list of tuples, technically a generator of a list of tuples, but it will return a list of tuples on which we can iterate, right? So that's why we're getting this key value. We're unpacking a list of tuples. The first item in the tuple is a key. The second item in the tuple is a value. And if I do this, I think we should get something that's a little more readable. So this is kind of wild. Look at this output. This is the same as our theoretical distribution. Oh, I think there's something wrong here. Yeah, okay. Bin list, bin D. Okay, so let me just make sure that this is doing what I think it's doing. Bin list. Oh, no, it is. It is. Okay, yeah. Sorry, it seemed unlikely that it would give us the actual theoretical distribution. But it's not that unlikely, as it turns out. It did it on the second try. But now look, we didn't even get a zero draw. We didn't get a zero count in this next run. And if I run this again, we got 0 through 4, but that distribution looks skewed, right? It doesn't look clean the way our theoretical binomial distribution did. So there's a way that we can make this look more like the theoretical distribution. And I'm going to have to change something here. Instead of printing out all these asterisks, I'm going to just print out the counts themselves. And I'm going to increase the number of samples. So I'm going to change this from 16 to, I don't know, let's do 1,000. if I do this, this is, we're not dealing with the same counts anymore, right? Because we're doing more than 16 samples, but we're getting something that looks, if you imagine this, it looks like that kind of normal-ish distribution or the binomial distribution, if you imagine these being counts heading out. So this is giving us something that looks more and more like our theoretical distribution, which is cool. And we're taking a random sampling approach. So something to notice here, the middle value is our most common value, and that's going to be true. That's going to be true of binomial distributions. So I'm going to do a different length. I'm going to do 8-bit binary, and let's see what that looks like. So again, we get this nice roundness here, and our middle value is our largest value. So essentially, what we did here is we created a random sampling approach to observe a phenomenon. And I like to think of this as being a natural phenomenon. I mean, yeah, it's happening digitally, but we are pulling random numbers, or at least pseudo-random numbers, and we're looking at, we're analyzing the results of that. And what we're seeing is something that is a natural phenomenon. And if we ran this, let's say we run this 10,000 times, and we average these numbers, these will look more and more they'll look more and more, how do I say this? They'll settle, okay? If we take the average of running this 1,000 times, these numbers will start to settle. And we'll have very little in the way of the numbers varying between attempts. So this has been kind of a crash course